Welcome to another many-body gravitational simulation video. In this video, I will depart from the usual Newtonian physics simulation of many-body systems to examine modified Newtonian dynamics, or MOND physics. Professor Milgram proposed MOND in 1983 as a way of understanding the flattened velocity rotation curves seen in galactic stellar orbits, without the need for dark matter. MOND has been in the science news recently, and my curiosity led me to create a MOND provision in my simulation. My intent was to study this theory and its ramifications on many-body systems. Since the original intent of MOND was to be able to create circular orbits in galactic systems, I thought my first foray into MOND should be to demonstrate this capability with my simulation. As such, the video today is a simple demonstration of circular orbits using MOND physics. In what follows, I will describe the current simulation, then I will show the evolution of the system over time and discuss its behaviors, and if you're interested in a brief overview of MOND, wait until the end and I will describe the implementation within the simulation code. Let's get started. In this simulation, as you can see, I present a flattened galactic disk of 5,000 stars. Each star has a mass of 1 solar mass. For a better perspective on this distribution, let's rotate this about the y-axis while I describe the rest of the system properties. The maximum orbital radius for any star is 600 parsecs, and this plot is 1,300 parsecs edge to edge. The minimum orbital radius for a star is 30 parsecs. Stars are uniformly distributed within this flattened disk, with the addition of a central mass of 1 million solar masses to emulate a central black hole. Note that the distribution here has a central bulge in the z-axis direction which flattens out with distance from the origin. All stars are given a velocity perpendicular to their initial radius vector. For close encounters, force softening is used within my code to overcome potential infinities. Here the force softening length is 0.8 of a parsec. Let's start the evolution of these stars. Notice as time advances, the stars in the exterior orbits are nearly circular. Interior orbits are perhaps not as noticeably circular. Since the initial velocities are perpendicular to their radius vectors, some z-axis mixing is expected, especially in the interior bulge. As evidence of mostly circular orbits, there appears to be no mixing of orbital radial shells during the simulation period. Also, the close encounter logs indicate that there are only 41 such events recorded. Note that close encounters are ones where the distance between two objects becomes less than twice the force softening length. It takes about 200 million years for this demonstration of circular orbits. I consider this a successful demonstration of the MOND implementation within my simulation code. Future videos are planned to study other gravitating systems. At this time, I'd like to talk a little bit about the MOND physics used within my simulation. First, we need to do a quick review of Newtonian gravity and the acceleration of a particle moving in a field of many particles. Here the equation you see is merely just the sum of all the accelerations of two-body accelerations between all the particles. Note that this is a vector sum in three-dimensional space. Here g is a universal gravitational constant, m is a particle mass, and r is a vector in the coordinate system that you're using. In 1983, Milgram published his first papers on MOND. In MOND, the actual acceleration, which we'll use little g, is related to the Newtonian acceleration by the following relationship. Here, a0 is a constant that Milgram calls a universal constant, and its value that is used within the simulation is 1.2 times 10 to the minus 10 meter per second squared. Mu of x is called the interpolation function, and it is unitless scalar function while the accelerations are the usual vector quantities. The choice of mu of x allows one to transform the above equation into a new equation, which is more useful within the simulation. Nu of z is called the inverse interpolation function, and this function allows one to determine particle accelerations based on Newtonian accelerations and the choice of that function. For my simulation, I have chosen the interpolation function that's known as the standard form in the wiki address below. This standard form can be recast to an inverse interpolation function as the following. These two equations on the page allow one to compute MOND accelerations for a system of particles. Before a simulation is finalized, one must pick or determine the initial velocity vectors for each particle. For Newtonian-only simulations, I use the following for the magnitude of the velocity. Here g is the universal gravitational constant. M is the interior mass out to that position vector r, and epsilon can be thought of as an eccentricity. For MOND, Milgram put constraints on the maximum velocity for large r. Here, velocity to the fourth power is a constant and equal to g times the total mass times our acceleration constant, a0. With the above constraint, one can determine an initial particle speed with the MOND constraints. Here, it is identical to the Newtonian case with the addition of the inverse interpolation function evaluated at the initial particle acceleration. The above is used within the simulation to determine particle speeds and reduces to the Milgram constraint equation for large distances. Also note that since this is a speed, the direction of the particle for this simulation were all perpendicular to the radius vector, which ultimately defines our velocity vectors for each particle.